All right. Hey, everyone. Thanks for virtually attending my talk. My name is Peter Attia. I'm currently a data analyst at Tesla, but today I'll be presenting work unrelated to my work at Tesla. This is a talk I'm giving on behalf of Steve Harris called Revisiting the 2 to the 1/2 Dependence of SEI Growth. This work was published around a year ago. You can find the DOI link down here. And yeah, without further ado, let's get started. So, as I'm sure most in this audience are aware, SEI growth is pretty complicated. Got heterogeneous growth, all sorts of reactions and products being formed. And we'll get into some of the other complications as we go. Yet, despite all that, the 2 to the 1/2 model is pretty widely accepted by the battery community to describe SEI growth. And the justification for the 2 to the 1/2 model is generally twofold. The first is theoretical. So SEI growth has some similarities to one-dimensional diffusion-limited growth. And the second is empirical. The fits to data often look good. So if you look at a typical capacity fade curve, it'll roughly correspond to the 1/2 growth. The question we're after in this work, though, is how convincing is this evidence? So both theoretically and empirically, can we trust the 2 to the 1/2 model to describe SEI growth? Let's start with the theory side here. We'll start by looking at classical thin film growth. So this cartoon is showing silicon dioxide growth on silicon. And at long times, once the thickness of this silicon dioxide layer has exceeded some critical value, this system will be transport fluid. So there's a few different reactants here, or concentration terms here. There's the oxygen in the ambient environment that has a concentration of C0. There will be a transport gradient from C0 to this interface, the interface of SiO2 and silicon. And there'll be a lower concentration of oxygen that reaches the surface here. There's a few different fluxes here, but at steady state, the diffusion flux will equal the reaction flux. And with some simple algebra, you can find that the thickness of this silicon dioxide layer does indeed scale with 2 to the 1/2 at steady state. So that model, often known as the Deal-Grove model for the authors that originally created it, that model is, of course, very widely accepted for describing thin film growth. But if we take a look at SEI growth, it can be quite different. So one still open question in the SEI community is its growth limited by transport of solvent or electrons? So instead of oxygen diffusing through the silicon dioxide layer, is it solvent or electrons? And this has a pretty big impact on the growth law and the growth scaling for the SEI layer, because of course electrons are charged and solvent is not necessarily. And if we are looking at the transport of charged species, we also have to account for migration, which complicates the picture quite a bit. We also have multiple growth regimes of SEI growth. So there's the initial formation versus the sort of long-term growth. There might be some convolutions with different transporting species in those different growth regimes. SEI growth is also heterogeneous. So this sort of compact porous layer morphology difference in the SEI is pretty well documented. An important point that I'll spend more time talking about in the next slide is that unlike in the silicon dioxide case, the reaction potential, which is the driving force for that reaction, that potential is changing dynamically with cycling and with storage or self-delithiation. I'll come back to that point in the next slide. So given all the complications, it is unlikely that SEI growth will be described simply by the 2 to the 1/2 model. Now, let's go a bit deeper here. There's really 3 different kinds of SEI growth. The first is electrochemical. So this is an electrochemical reaction in which the electrons and the lithium ions are coming from separate sources. So this is pretty common during cycling. You have lithium ions reaching the surface of the, say, carbon substrate, carbon electrode, and the electrons are coming from the electrode, and they meet basically at the SEI and form more SEI. Second type of SEI growth is chemical SEI growth. So this is a chemical reaction where the lithium ions and the electrons are coming from the same source. They're essentially a neutral lithium in the carbon electrode, and they're reacting with EC to form SEI, or whatever solvent that they're reacting with. So this is basically a chemical deinsertion interface because the lithium ions are deinserting from the electrode and reacting to form more SEI. And the last is thermal. This is a kind of edge case, but still important to think about. This is essentially when a lithium salt, say LiPF6, can decompose into, say in this example, PF5 and LiF. This is a separate mechanism for SEI growth, but this can contribute to the growth of this actual mechanical growth of the SEI layer. And in this case, it's an inert interface because the electrode itself is just sort of the resting place for the product, but it's not participating in the reaction. So there's these three types of growth, and electrochemical growth, an important thing to note here is during cycling, the electrochemical potential of these electrons is changing wildly throughout the cycle. So if your graphite goes, say, simply from 1 volt to just above 0 volts, the driving force for this reaction is changing dramatically throughout that cycle. And at some points at high potentials, the reaction may not even be favorable. This is a pretty significant difference from field growth kinetics. And it's really hard to picture a scenario in which electrochemical SEI growth would actually follow that mechanical, or those mechanics and that growth law. Thermal SEI growth, of course, has no real dependence on any parameters other than temperature. So this is not expected to follow the 2 to the 1/2 growth. This would be linear growth, if anything. Chemical growth is a bit different. So chemical growth is most like Diel-Grove in that Diel-Grove is also a chemical reaction. The main difference here is, again, as lithium is leaving the electrode, the electrochemical potential of the remaining lithium ions is decreasing. So the fully charged lithium ions are going to be more reactive than the lithium ions in the electrode when it's less fully charged. So bottom line here is only chemical SEI growth, which is more similar to storage growth, even slightly resembles the Diel-Grove kinetics. Thermal SEI growth is quite different, more of an edge case. The electrochemical SEI growth, which is most common during cycling, has these really widely varying driving forces, and it's not at all at steady state. So theoretically, we can't think about electrochemical SEI growth or cycling SEI growth as following 2 to 1/2 growth laws. So to wrap up the theory here, we always assume this transport limited growth, which is based on the apparent 2 to the 1/2 kinetics. And if we kind of step back and think about it, we have this single super simple model for all these different processes across multiple chemistries, temperatures, geometries, et cetera. And there's really not much theoretical justification for this. Down, and there's more details in the paper if you're interested. The storage SEI growth is the most similar chemical SEI growth, but still has some differences from the conventional theoretical scalings here. So all that said, maybe to some extent, who cares? If you're a industry person, say like me, maybe you just want to get the good fit and you don't necessarily care about the theory. So let's turn to the empirical side here. Are the 2 to the 1/2 fits in literature actually justified? So what we did here is we looked at 7 different data sets measuring SEI growth. 6 of them were previously published, and 1 of them is a new data set introduced in this work. And we had a 4-fold strategy here to try to determine whether these fits were actually justified. The first step here is to compare multiple models for each set of data. So we looked at a few different power law models to see if we could get better fits with different models. We also look at the confidence intervals, specifically 95% confidence intervals of the fitted parameters. So for the power law models that we use, we try to see if 0.5 is within the bounds, the error bounds of the parameter estimation from the fit. Third point here is we use the adjusted R-squared value. So R-squared is a helpful metric, although I'll talk in the next slide about some of its pitfalls. The advantage of adjusted R-squared over simple R-squared is that R-squared adjusted penalizes overly complex fits and fits with additional parameters. So if a 3-parameter fit does better than a 2-parameter fit, as it will, but the additional R-squared gain is minimal, the R-squared adjusted will penalize the overly complex fit. And the fourth step here is residual analysis. So this is super important, and I'll illustrate that more on the upcoming slides. So a big point here is looking at like interpolation versus extrapolation. We'll start by looking at interpolation and seeing then how we can use these models to extrapolate and do more of like time prediction type stuff. So let's back up a second, just think about, what does it mean to get a good fit? I think a very common practice in many scientific communities, the battery community included, is to fit data to the T1.5 model by eye or by using a high R-squared. And for a lot of reasons, a high R-squared is not the best way to evaluate if a model fits the data. So here's an example. So I generated a data set of following y equals 5x to the 0.3. And that's the black dots here. So this is not a T to the 1/2 model. I then fit this data to a T to the 1/2 model, x to the 0.5. And that gives a straight red line here. We can see that the parameters are pretty different. So this is really a 2-parameter model. This is also a 2-parameter model, but we've constrained the exponent to 0.5. We can see the parameters are quite different, but kind of interestingly, the R-squared is very high. R-squared is 0.99. So to some extent, this seems like this would be a good fit. What we're really looking for here is how well will this extrapolate to longer time, which is, of course, a primary interest of looking at developing these types of models. So what we do here is what's called residual analysis. And quite simply, we just subtract the true observation of y, and from the prediction. So the prediction is y hat, has a little caret on top. And what we see is this systematic trend in the residuals. And this is sort of a smoking gun to say that the model is not really capturing the true trend in the data. There's some additional source of complexity that the model is not capturing. So a good fit, as I would define it, is a fit that has no trends in the residuals. The residuals just have sort of scattered around the 0. Okay, so let's get into it. What I'll be doing is basically flashing different literature, data set, and then reviewing how well it fits. So this is an older paper from Broussely. This is one of the first references that I've seen to achieve the 1/2 model in full cells. This is looking at capacity loss during storage in full cells. And you can see from this top plot here that this is a 1.5 years or so of storage, so quite a good bit of data. And it's measured at both 30C and 60C. What I've done here, and hopefully it's not too small on your screen, is fit these curves to 3 different models. One is a t to the 0.5 plus b, so we constrain the exponent. The second is a t to the b, so there's no, or sorry, a t to the x, there's no b term here. And the third is this full equation here, so a t to the x plus b. So that's a 3-parameter model. If you look at the exponents here, we're seeing that this 30C one is outside of the range of 0.5. So 0.5 does not fall from the confidence bounds of this parameter. And if you look at the residuals here, they are pretty scattered around 0, but they're still a bit noisy and a bit large. The 60-degree data actually is, to give away the lead a bit, the only data set out of the, I think, 17 that we evaluated, in which 0.5 does fall within the error bound. So the exponent value is 0.48 plus or minus 0.5. So 0.5 is well within those error bounds. So overall, this is not bad and pretty close, but still not perfect, especially for the 30 degrees C data. This is another older data set, but from a well-regarded paper, Wright et al. From 2001. This one is a bit different in that it was looking at resistance growth during storage in full cells. And I think it was looking at 40C, 50C, and 70C. I just included 2 of the temperatures here. The same exercise, because the initial resistance starts at 35, the model without an intercept term, so the second model here, has this really poor trend in the residuals, but that's okay, it's kind of expected. If you look at the 3-term model, 0.5 is just outside of all of these exponents, so with a 95% confidence interval. So this would be 0.51, 0.51, and then 0.53 in the lower bounds of these parameter estimates. So technically, to the 0.5 is not well represented by these models and by this data, but it's quite close, so it might be okay. Okay, so those were both storage data sets. There's maybe some cycling data sets. This is a paper from Jeff Don's lab, Aaron Smith et al., 2011. And this was one of the seminal papers in describing high precision coulometry. Of course, is a technique Jeff Don pioneered. So this is a nice paper in that it's designed to accurately measure SEI growth in lithium graphite half cells. So same exercise here. This is total irreversible capacity, QIRR. So this is the difference between the charge and discharge capacities with cycle number. And if we look here, actually, the 2½ model has a very systematic trend, or a highly systematic trend in the residuals. So this looks very similar to the example we gave earlier. And even the higher temperature ones, it's less dramatic than the 30C one. Yeah, this is a 50C data. This one, all of these models have pretty clear trend in the residuals. So it seems like this simple power law model is not capturing the data well. But if you look at the exponents for all the temperatures here, they're much lower than 0.5. So 2 to the 5 is well outside of these, and the residual appear off. So this, long story short, this data needs to be summarized by a different type of data set, different type of model. So here's another paper from Smith et al., kind of confusingly, also in the same year, but this is another Jeff Don paper. This is looking at one full cell. So measuring capacity loss for a full cell. This is just around 50 cycles. For this one, we can see a pretty clear trend in the residuals for all of these models. So none of them are quite capturing the data well. The 0.5 model, the green one, and the purple one, the 3-term with the floating exponent, are pretty similar in terms of residuals. For this 3-term model, the exponent is 0.48 plus minus 0.01. So again, just outside, arguably acceptable, but a bit different. This is another paper from Jeff Don's lab. This was pretty notable in that the cell was cycled for over 10 years, close to 10 years in the case of this red one. Again, for the cycling data set, the exponents are quite low compared to 0.5, and 0.5 is well outside the errors. And we can see pretty clearly in all of these the systematic trend of residuals. So especially for this group 4 cell, this is again sort of the classic parabola shape that indicates that we're not truly capturing the fit to the data here. Okay, this is a data set from a paper I wrote around 2 years ago or so. This is looking at capacity loss during cycling of carbon black half cells. The reason for carbon black is it's a high surface area carbon material, so it grows a lot of SEI. So in theory, it's easier to measure the SEI. That said, of course, there could be some differences with graphite, so that's one thing to keep in mind when looking at this data. We look at the A2, the X models, the ones with the 3 terms were quite strange, but exponents here are very low, 0.2-ish for all of them. These are 3 triplicate cells. And for all of them, we can see, again, the pretty clear systematic trend in the residuals. So same story here, but very far from 0.5. Okay, and lastly, this is a new data set looking at capacity loss during storage of carbon black half cells. So this is essentially a measure of self-delithiation. So without getting too detailed into the method here, the idea is that if we measure the voltage versus time trend for the self-delithiation, and we know a recent delithiation, if we have a recent delithiation cycle, Q versus V, we can combine the Q as a function of V and the V as a function of T to get Q as a function of V as a function of T, or Q as a function of T. That was a bit of a mouthful, hopefully you caught it, but this is basically the measure of the self-delithiation capacity as a function of time. So keep in mind that during this delithiation, the voltage of the cell is changing because lithium is leaving the carbon black. So the driving force should be changing with time. So if we look at these cells, they look roughly 2 to 1/2-ish, but again, same story. We have quite high confidence in the exponents here, and it looks like as we get to higher temperature, excuse me, as we get to higher temperature, the exponent is closer to 0.5, but still well outside of it. And these data also have systematic trend residuals. Okay, so we went through a lot of different data sets there. The key thing here is that only one of the 17 series had a fitted exponent that was technically within 0.5, where 0.5 was containing the 95% confidence interval. Many of these were close, but close here does not equal correct. And again, we're trying to see if these models are actually empirically justified. And while some were close, many were not. So some of these data sets had exponents as low as 0.2. So in general here, it seems that 2 to the 1/2 generally fits storage data better than cycling data. And that's not too surprising given what we were discussing earlier in terms of theoretical justification. So for storage, this is much closer to the ideal growth kinetics than cycling, in which things are very out of steady state. And the 2 to 1/2 dependence can't be theoretically derived. Okay, more models. We only looked at 3 different power law models and evaluating those other data sets. So an open question here is, do other models work better? So this is 9 different models. This is fit to one of the Smith et al. Data sets, I think with the UHPC measurements. And if we look at all of these, we have pretty high R-squared adjusted for all of these. Some of these are as high as 1.000. But if we look at the residuals here, there's always a trend in the residuals. So none, maybe for one like this, it looks not as dramatic as some of these other ones, but there is always some sort of trend in the residuals here. So it seems that none of these sort of simple, up to 4 parameter models are really capturing the true physics here. And again, that's kind of expected because SEI growth is really complicated. Another thing we wanted to explore was looking at moving window averages. So the thinking here is SEI growth may change as a function of cycle number, and the growth dependence could change as a function of cycle number. So this is 4 different data sets. I don't remember off the top of my head which 4 we're looking at here, but the idea is that this is looking at 7-point moving windows and looking at, as we shift that window, how does the exponent change? So as a whole here, for most of these data sets, the exponents don't change much with cycling, which kind of suggests that there's not dramatic changes in growth behavior. The one exception was this data set. I apologize, I don't remember which data set this is offhand, but there's some trend here where the exponent drops from 1.2 down to 0.6. And lastly, I think we want to think a bit about prediction here. So obviously a big motivation for understanding the growth dependence is to extrapolate. So, maybe you could say, okay, who cares about 0.45 or 0.5, but to predict very long lifetimes, these subtle differences can make a big impact. What we did here is we took this Smith et al. Data set, again, another UHBC data set, and we fit the data to the first 15 out of 19 data points in this trend and looked at the error for the remaining 4. So this is sort of simulating what we would be doing if we were extrapolating. But instead, we're looking at less data and seeing how the extrapolation holds. And what we see is if we look down here, for the 2.5 model, we can see how the error is growing with increasing time or increasing cycle number. And eventually, we're outside of we're not predicting the target, even with the error bars. Actually, it looks like with this one, only the, A2 to the B model ends up actually having the error within the error bars here. Even the 3-term model is not doing as well. And if we look at this plot up here, we can see how these different extrapolations can lead to pretty different estimates of the overall SEI growth at longer times. So the predicted capacity loss at 1,000 hours for this data set is 66% larger for the 2.5 model than for this 2-term model, the blue model here. So this can indeed have quite a large impact on lifetime predictions. All right, so wrapping up. As a whole, our conclusion is that the 2 to the 1/2 model is not well supported by theoretical and empirical evidence. What are the implications of this? There's a lot more I think we can learn and develop in terms of improving SEI models. And there's certainly a much richer and more complex understanding that is out there that we can try to understand. And from a practical point of view, we need to understand how SEI grows to generate more accurate lifetime forecasts. Now, all that said, we bashed this, humble 2 to the 1/2 model pretty intensely here. What should we use instead is the natural next question. Unfortunately, I have a pretty unsatisfying answer, which is we don't know. But if you do use 2 to the 1/2, you have to use at your own risk, knowing the limitations here. And really, I think this is an opportunity for both the modeling and experimental fields to work together and hone in on a more accurate representation of this complex phenomenon. All right, thanks for listening. If you have any questions about this work, feel free to contact me at this email address here. I also have to give an obligatory Tesla plug. If lifetime prediction and other problems related to extrapolation interest you, Tesla is hiring. So if this is of interest, please contact me at my Tesla email, Fathi@tesla.com, with your resume. Thanks everyone for your time, and hope to hear from you soon. Take care.